Welcome to TalkTensors.
It's really good to be here today.
Yeah, today we are doing something a little specialized. We are opening up the archive.
Dusting off the classics.
Exactly. We are rewinding the clock to a moment that, from our vantage point sitting here in 2026, it feels simultaneously ancient and, like it just happened yesterday.
I mean, the pace of the field makes 5 years feel like 5 decades.
It really does. So for you listening, today's deep dive is into the paper that effectively ended the era of generating images being hard.
And started the era of generating images just being a matter of massive brute force scale.
Right. The pivot point, the moment the machine finally learned to dream.
Or maybe hallucinate convincingly on command is the better way to put it.
I like that. We are talking about the seminal paper, Zero-Shot Text-to-Image Generation. This is the work from the team, including Aditya Ramesh, Mikhail Pavlov, Gabriel Go, Ilya Sutskever, and several others.
Published right around early 2021.
Which is almost quaint to think about now. I mean, we live in a world where high-fidelity image generation runs natively on the phone in your pocket.
Yeah, but this paper is the foundation. It's the bedrock.
It's the moment the transformer architecture, which, had already completely eaten the world of natural language processing with models like GPT-3, it finally opened its mouth wide enough to swallow computer vision whole.
If you want to understand anything running today, you have to understand the architecture they laid out here.
So let's set the scene for everyone. The year is 2021. What did the pre-transformer vision landscape actually look like? Because it wasn't a total wasteland. We had image generators.
Oh, absolutely not a wasteland. It was incredibly active, crowded even, but it was completely dominated by GANs.
Generative adversarial networks.
Right. And VAEs, the variational autoencoders. And while they were brilliant pieces of engineering, they were, let's call them fussy.
Fussy is definitely a polite word for it.
They were just incredibly fragile. Take a GAN, right? You have a generator network trying to fool a discriminator network.
It's a mini-max game.
Exactly. Yeah. A very delicate equilibrium. If one of those networks gets too strong too quickly, the other one just collapses.
Yeah.
You get absolute garbage out.
And they suffered terribly from mode collapse.
Right, where the model essentially finds one single image that happens to fool the discriminator perfectly, and it just stamps out that exact same image over and over and over.
So beyond the training instability, they were also hyper-specialized, right? Like, if you wanted to generate a bird, you had to train a model specifically on the CUB200 bird data set.
Yeah.
And if you wanted a flower, you trained a completely separate model on flowers.
There was really no such thing as a general-purpose generator. If you wanted to create a complex scene, say, a dog sitting on a couch, you couldn't just do it end-to-end.
You had to build a whole Rube Goldberg machine.
You really did. Step 1, you generate a scene layout or maybe some bounding boxes. Step 2, you generate object masks inside those specific boxes.
Step 3, bring in the jam to fill in the textures.
It was so heavily engineered, you basically had to hold the model's hand every step of the way.
Because the underlying assumption in the field was that the semantic gap between the word dog and the actual matrix of pixels representing a dog, it was just too wide to cross in one jump.
Precisely. Researchers spent years just trying to build bridges halfway across that gap, finding better modeling assumptions for very specific fixed data sets.
And then this paper drops, and it asks the burning question that was essentially haunting everyone after GPT-3 came out.
Which is, what if we just stop building bridges?
What if we just train a big enough transformer to jump the entire gap?
Yeah. Treat the pixels like text.
Which brings us to the core thesis of this deep dive. If we have to summarize this entire paper in one breath, it is this. The authors proved that if you treat image pixels exactly like text tokens and you scale the model massively—
12 billion parameters.
Right, and you train it on massive data—
250 million pairs.
Then a single autoregressive transformer can learn to generate high-fidelity images from text with zero-shot capability.
Effectively ending the need for all those specialized components. No object labels, no segmentation masks.
Just, here is some text. Predict the image tokens that come next.
It's a radical simplification.
So today, we are going to unpack exactly how they pulled this off. We'll dissect the two-stage training methodology, the DVAE and the transformer.
We need to get into the math of the evidence lower bound, too. The ELB.
Oh, we will. I know you love the ELD. We'll also cover the engineering nightmare of distributed training. I mean, how do you even fit a 12 billion parameter model into GPU memory in 2021?
It wasn't easy.
And we'll look at the quantitative results where it just completely dominates the GANs of the era. And finally, the qualitative magic.
The variable binding.
Combinatorial generalization, where the model starts doing things it wasn't even strictly programmed to do.
And of course, we wrap up with the novel notions segment.
Always.
Oh.
Okay, let's get into section 1, the problem and the pivot. You mentioned earlier that the status quo was all about finding these careful modeling assumptions. Why was the idea of just treating pixels like text considered so intractable for so long?
It all comes down to cost. The computational cost of a pixel versus a word.
Right?
In NLP, a sentence is maybe 50 tokens. A long paragraph is a few hundred.
A transformer can handle that easily.
Easily. But an image, even a really small image, say 256 by 256 pixels, that is over 65,000 pixels.
And each of those pixels has 3 color channels.
Red, green, and blue. So now you are looking at nearly 200,000 discrete data points for one single low-resolution square image.
And the core mechanism of a transformer is attention.
Exactly, self-attention. And the mathematical reality of self-attention is that its computational cost scales quadratically with the length of the sequence.
Big O of n squared.
Right, so if you double the sequence length, the compute required quadruples.
So if you try to feed 200,000 raw pixels into a standard transformer,
the attention matrix becomes hundreds of billions of entries.
You would run out of VRAM before you even finished compiling the first layer.
It is physically impossible, or at least it was hardware impossible at the time. You simply cannot treat raw high-res pixels as a flat sequence for a model of that scale.
So the memory bottleneck was the giant wall keeping transformers out of the vision space.
That was the primary physical wall. But there was also a theoretical wall regarding the nature of the data itself.
Tell me about that.
Well, these autoregressive models learn using likelihood objectives. They are essentially trying to predict the exact next value perfectly.
Right.
The problem with images is that likelihood objectives tend to heavily prioritize high-frequency details.
By high frequency, you mean the tiny, rapidly changing details, like the exact noise pattern of the grain in a photo.
Exactly. The texture of a single blade of grass.
Mm-hmm.
The exact hex code of a pixel compared to his neighbor. It cares intensely about that local texture.
But to a human looking at the image,
the meaning is in the low-frequency structure.
The overall shape. Is it a dog? Is it a car?
Right, so if you just feed raw pixels, the model could easily waste 90% of its parameter capacity just memorizing useless high-frequency texture noise and completely miss the actual shape of the object.
It misses the forest for the microscopic details on the bark of one tree.
Precisely. So the authors realized they needed a way to compress the image, but a very specific type of compression. They needed to strip away the high-frequency noise without losing the semantic meaning of the shapes.
They needed to turn that massive, noisy grid of 200,000 pixel values into a short, meaningful sequence of image words.
Which brings us perfectly to section 2, the methodology.
The 2-stage training process. Let's break down stage 1. This is the discrete variational autoencoder, the DVAE. What is the actual goal here?
The goal is to take that 256 by 256 RGB image and squash it down into a 32 by 32 grid.
Okay, so a 32 by 32 grid. That is exactly 1,024 tokens.
Yes, from nearly 200,000 values down to 1,024 tokens. It is a staggering compression ratio.
But the key word here is discrete. They aren't compressing it into continuous floating point numbers, right?
Right. In a traditional autoencoder, your latent space, the compressed bottleneck, is usually a continuous vector, a bunch of decimals.
But a transformer expects discrete tokens, like words in a dictionary.
Exactly.
Yeah.
So this DVAE learns a discrete vocabulary of visual concepts.
The paper states the vocabulary size is 8,192.
Yes. So imagine you have a visual dictionary with 8,192 distinct symbols. Now, we don't know exactly what those symbols translate to in human English.
It's an alien language.
Completely. But mathematically, one of those tokens might represent, say, a sharp vertical edge. Another token might be a specific gradient of blue texture. Another might be the curvature of an eye.
So the DVAE's encoder scans over a patch of the raw image and decides, okay, this specific patch is best described by token number 402 from our visual dictionary.
Exactly. It translates the whole image into a paragraph of exactly 1,024 alien words.
And suddenly the memory bottleneck is gone.
Completely bypassed. A sequence of 1,024 tokens is trivial for a transformer to process.
But wait, training a discrete model is notoriously tricky. Because you can't easily do backpropagation through a hard choice.
The non-differentiability problem.
Right. If the encoder has to make a hard choice between token A and token B, that creates a step function. The gradient just stops dead. You can't take the derivative of a discrete choice.
You cannot. So how do they trade it? They use the Gumbel softmax relaxation.
Which is such an elegant mathematical trick. Can you explain how it works in this context?
Sure. It essentially allows the model to be soft during the training phase.
Soft meaning it hedges its bets.
Exactly. Instead of rigidly picking just one token, the encoder outputs a weighted probability mix. It says, I am 60% sure this patch is token A, 30% sure it's token B, and 10% token C.
And because those are continuous probabilities, they are differentiable.
Right. The gradients flow perfectly through that soft mixture. But you still ultimately need discrete tokens for the transformer. So as the training progresses over time, they anneal the temperature of that distribution.
Annealing? Like when you cool metal slowly to make it structurally harder?
It is the exact same concept mathematically. As the temperature parameter drops towards 0, that probability distribution gets sharper and sharper.
So that 60-30-10 split becomes, say, 95-5.
And eventually it becomes effectively 99.9% token A.
So it forces the model to gradually make a hard, discrete choice, but it provides a perfectly smooth, differentiable ramp to get there.
It is brilliant. It stabilizes the training of the visual dictionary.
Okay, so that is stage one. We have our DVAE trained and ready. It can reliably translate any raw image into 1024 discrete image tokens. Now we move to stage two, the main event.
The autoregressive transformer.
This is the 12 billion parameter beast.
It is a decoder-only architecture, very, very similar to the setup of GPT-3.
And the input sequence to this transformer is a concatenation. We literally just stick the text and the image together.
Yes, you take the text caption, which they encode using byte pair encoding, BPE, capped at a maximum of 256 tokens.
And you just append the 1024 image tokens right to the end of it.
Right, so your total stream of data is up to 12,280 tokens long. Text tokens first, immediately followed by the image tokens.
And because it's an autoregressive model, it is essentially just playing the world's most complex game of autocomplete.
That is all it's doing. It reads the text caption, builds an internal representation of that text, and then it tries to predict the very first image token.
Then it looks at the text, plus that first image token, and guesses the second image token.
Token by token, left to right, top to bottom, across the image grid. It models the conditional distribution of the image, given the text.
Now, there's a specific detail in the paper about their padding strategy that I found really interesting. Usually in NLP, if your caption is short, say it's only 10 words long, you just mask out the remaining text slots, right?
Yeah, you just pad with zeros or set the attention weights to negative infinity so the model completely ignores them.
But the authors here did something highly unusual. They actually learned a unique special padding token for each individual text position.
Yes, all 256 text slots have their own specific learned padding embedding.
So if my caption ends at position 10, the model doesn't just see a void for the next 246 slots. It sees 206 uniquely learned dense vectors.
Exactly.
Why do that? On the surface, it almost sounds like you're just injecting noise into the context window before the image starts.
It does seem counterintuitive. And the authors actually mentioned that during their preliminary experiments, using these learned padding tokens resulted in a slightly higher validation loss.
Which is usually a bad thing.
Normally, yes. But they noticed that despite the higher loss, it resulted in significantly better qualitative performance when dealing with out-of-distribution captions.
Interesting. So captions that look very different from the training data.
Right. The working theory is that forcing the transformer to process these dense learned padding tokens gives the network a standardized processing buffer.
Like a moment of silence to internally stabilize its hidden states before it has to start rendering the image.
A runway, yes. It calibrates the network dynamics so that by the time it hits token 257, the first actual image token, the internal activations are in a very predictable, stable regime, regardless of how short the actual text prompt was.
That is a fascinating engineering hack. It's not necessarily pure math, it's just observing the empirical behavior of a massive nonlinear system.
A lot of deep learning at this scale is essentially alchemy.
Let's actually talk about the pure math for a second, though, because the paper frames this entire two-stage training procedure as maximizing a specific objective, the evidence lower bound or the ELB.
Yes, on the joint likelihood of the data.
Can we unpack the same equation here? Yeah. It is P sub theta, Ci's of x, y, z equals P sub theta of x given y, z times P sub pi of chi phi z a, Okay, let's break that down for the listener.
I'd be happy to. So we are trying to model reality. And in our case, reality consists of 3 variables: the actual raw image pixels, which is X, the text caption, which is Y, and the discrete image tokens, which is Z.
Okay, X, Y, and Z. Pixels, text, tokens.
Right. We want to maximize the probability that our model generates the real-world data we observe. But calculating that directly is intractable. So the equation factorizes the problem into 2 distinct manageable pieces.
Okay, what is the first piece?
The first piece is P subtext I O high of Y O Z. This is the prior. This is exactly what the transformer is learning.
It's the probability of the text and the tokens existing together.
Exactly. The transformer learns the complex joint distribution of text prompts and their corresponding visual token sequences. It learns which alien visual words make sense given the English words.
All right, and the second piece?
The second piece is P sub theta of X given Y Z. This is what the DVAE decoder learns.
The probability of getting the exact real pixels, X, given the text Y and the token Z.
Right. Though in practice, the DVAE decoder usually ignores the text Y and just reconstructs the pixels X entirely from the tokens Z.
So maximizing the ELB is effectively a handshake agreement between the 2 separate models.
How do you mean?
Well, the ELB objective usually has a reconstruction loss term and a KL divergence term, right? The reconstruction loss is holding the DVAE accountable. It's asking, hey, does the image you decoded from these tokens actually look like the original raw image?
Correct. It ensures the tokens actually contain the necessary visual information.
And the KL divergence term is holding the transformer accountable. It's asking, hey, are these specific tokens actually predictable given our text prior?
Exactly. By optimizing this lower bound, they force the 2 systems to cooperate. The DVAE is forced to create a language of tokens that the transformer finds mathematically easy to predict.
And the transformer is forced to predict token sequences that the DVAE can actually decode into something resembling reality.
It is a beautifully constructed closed loop.
It is. But none of this beautiful math actually matters if you don't have the data to feed the loop. Which brings us to section 3, data and engineering at scale.
The fuel for the fire.
Right. Now, in 2021, the standard benchmark for this kind of work was MS COCO. But they didn't train on MS COCO, did they?
Oh, no. MS COCO is tiny. It has, what, maybe 300,000 images?
Something like that.
That is fine if you are training a highly constrained, specialized GAN. But if you feed MS COCO to a 12 billion parameter transformer,
it would just perfectly memorize every single pixel of the dataset by lunchtime.
And then completely fail to generalize to anything new, it would be massively overfit. To train a model this size, you need orders of magnitude more data to cover the true statistical distribution of the visual world.
So they created their own data set, 250 million text image pairs.
Which is approaching the scale of Google's proprietary JFT300M dataset.
Where did they even source 250 million labeled images?
The internet.
Just scraping the web.
Essentially, yes. It's a massive combination of existing corpora. They use conceptual captions, Wikipedia, and a heavily filtered subset of YFCC 100M.
Yahoo, Flickr, Creative Commons.
Right.
But you can't just scrape 1 billion Flickr photos and Wikipedia alt texts and dump them straight into a transformer.
Yep.
The internet is mostly garbage.
Garbage in, garbage out. The data pipeline is arguably just as important as the neural architecture itself.
So what kind of filtering are we talking about?
Rigorous filtering. First, they removed any pairs with extremely short captions. If the text doesn't actually describe anything, it's useless for conditional learning.
Makes sense.
They used a package called CLD3 to aggressively filter out non-English text, ensuring the language prior remained consistent.
And what about the text itself? A lot of internet images have terrible metadata.
Oh, the boilerplate. Yes. They had to build heuristics to strip out boilerplate text.
You mean stuff like click here to enlarge or image 1 of 5?
Exactly. Because if you leave that in the data set, the model learns the wrong associations.
It starts thinking that the visual concept of a cat inherently includes the floating English text click to enlarge hovering next to its ear.
We've seen that happen in early generative models. If 10% of your training data has a Getty Images watermark on it,
the model learns that watermarks are a fundamental physical property of reality.
Yes, it assumes watermarks are naturally occurring phenomena, so cleaning that out is vital.
Okay, so you have 250 million perfectly clean text image pairs, and you have a 12 billion parameter model.
Yes. Let's talk about the hardware engineering, because you cannot just load a 12 billion parameter model into a GPU.
You couldn't even load it onto a single node of GPUs at that time.
Right. So this is distributed training. But the paper outlines a very specific, highly optimized distributed strategy.
It is really a masterclass in systems engineering. The fundamental bottleneck when you distribute a model across multiple machines is communication bandwidth.
Explain that for us.
Well, within a single machine, the GPUs are connected by something like NVLink. The bandwidth is massive. They can share data almost instantly.
Right.
But when a machine has to talk to another machine across the server rack, across a network switch, the bandwidth drops drastically. It's a massive choke point.
So how did they get around the network choke point?
They used parameter sharding. They sliced the model's parameters up and distributed them across 8 different GPUs.
Okay, so GPU 1 holds piece A, GPU 2 holds piece B, and so on.
Right. But the really clever part is the communication pattern they designed. If you look at figure 5 in the paper, it's laid out beautifully. Walk us through the forward pass.
Okay, so during the forward pass, you are computing layer by layer, while a GPU is currently doing the heavy matrix multiplication for, say, residual block 1.
It isn't just sitting there waiting for block 2.
No, it is actively prefetching the parameter shards for residual block 2 over the network.
So it's anticipating what it needs next.
Exactly. It uses an operation called all-gather. It reaches out to the other GPUs, pulls in all the missing pieces for the next block, and assembles them in memory just in time.
Just in time for the computation.
Yes. And then, and this is the crucial part for saving memory, the millisecond the computation for block 1 is finished, it deletes the assembled parameters for block 1 from its local VRAM.
Wow. So it never actually holds the full model in memory at any one time?
Never. It streams the model through the GPU layer by layer, continuously assembling and destroying the weights as it goes.
That is incredibly efficient. It's like a factory assembly line where the parts only exist exactly when the robotic arm needs to attach them.
It's a great analogy. And then on the backward pass, when they are calculating the gradients to update the model, they run the whole process in reverse.
So they're prefetching the previous block's shards.
Yes. And once the gradients are calculated, they execute a reduce scatter operation.
Reduce scatter. What does that do functionally?
It averages out all the gradients across the entire cluster of GPUs, but it does it in a way that at the end of the operation, each specific GPU only ends up holding the final average gradient for the exact parameter shard that it inherently owns.
It's perfectly synchronized.
It has to be. If even one GPU in the cluster lags by a fraction of a second, the entire pipeline stalls. Every machine is waiting.
They also note in the paper that they experimented with gradient compression, right? To further reduce that network traffic.
They did. They tried using techniques like power SGD, which is a low-rank approximation method, to compress the data during those all-reduced communication steps.
But they ran into some snags with it.
They did. They noted that using 16-bit precision caused significant numerical instability when combined with that compression.
16-bit precision, the classic ghost in the machine.
Always. When you are multiplying billions of very small numbers together, the rounding errors inherent in 16-bit floats just accumulate until the model diverges and explodes.
Still, the engineering required just to get this thing to train is staggering.
It is a triumph of systems design just as much as machine learning.
Okay, so they built it, they trained it. Let's talk numbers. Section 4, quantitative results. How much better was this autoregressive Titan compared to the GANs?
To measure that fairly, they evaluated it in a strict zero-shot setting on the MS-Kyoko dataset.
Meaning the model was never fine-tuned on MS-Kyoko. It never saw the official training labels.
Right. It was generating images purely based on its internal generalized understanding of the internet data it absorbed.
And they pitted it against the state-of-the-art GANs of the time, DFGAN, DMGAN, and ANGAN.
The heavy hitters.
So what happened in the human evaluations? Let's look at figure 7.
It was an absolute blowout, not even close. Human evaluators preferred the DALL-E output over the leading DFGAN. For realism, 90% of the time.
90%.
And for accuracy, meaning, does the generated image actually match the text prompt? They preferred DALL-E 93.3% of the time.
That is not a margin of error. That is a complete paradigm shift.
It essentially retired the competition overnight. It proved definitively that the hyper-engineered GAN approach was strictly inferior to the pure, massive scale of the transformer approach.
But, and there is a but here, there is a catch to these results, or maybe a feature, depending on your perspective. The model doesn't just confidently spit out one perfect image on the first try, does it?
No, it does not. And this is a vital part of their pipeline that often gets completely glossed over in the history books. They use contrastive re-ranking.
The automated cherry-picking algorithm.
Exactly. When you give the model a prompt, it doesn't generate one image. It generates a massive batch of n different samples.
And the paper identifies that n equals 512 is the mathematical sweet spot.
Right, so it generates 512 completely distinct images for a single prompt.
Yeah.
And then they bring in a separate, independently trained contrastive model, very similar to CLIP.
And this CLIP-style model acts as the judge.
It looks at all 512 generated images, compares them to the original text prompt, and ranks them based on semantic similarity. And it only outputs the absolute highest scoring image.
Figure 6 in the paper illustrates why this is so necessary, and it is honestly hilarious.
The urinals.
Yes, the prompt is, a group of urinals is near the trees at n equals 1, so literally the very first guess the model makes, the image is just a brown and white blurry smear. It's completely unrecognizable.
Just noise.
But then you look at n equals 8, the highest ranked out of 8 tries. It's getting slightly better. You can sort of see a tree shape.
And then at n equals 512.
At 512, you have an incredibly crisp, structurally perfect row of porcelain urinals sitting elegantly in the middle of a dense forest.
It perfectly captures the prompt.
But what does that actually tell us about the model's intelligence?
It tells us that the autoregressive generator is incredibly noisy and high variance.
It's throwing paint at the wall.
Yes. The masterpiece, the perfect image, is somewhere inside its probability distribution. But it is very rarely the most probable image right at the center of the curve. The generator is deeply creative, but fundamentally unreliable.
So you have to cast an incredibly wide net into the latent space to catch the genius.
Exactly. The transformer generates a massive amount of both brilliant signal and absolute garbage noise, and the contrastive re-ranker acts as the curator to filter out the noise.
Let's move to section 5, which focuses on the qualitative findings. This is the stuff that made the paper go completely viral.
The magic.
The magic. Let's start with combinatorial generalization. This is something that AI researchers have chased for decades.
The ability to take concept A and concept B, two things the model has never logically seen, combined in its training data, and fuse them logically.
The tapir accordion, figure 2A.
A classic. The prompt is a tapir made of accordion.
Now, a dumb model, a copy-paste model, would just find a picture of a tapir, find a picture of an accordion, and lazily slap them next to each other.
Or overlay them with 50% opacity.
Right. But this model does something profoundly different.
It actually alters the fundamental texture and geometry of the animal. It takes the pleated, folding bellows of the accordion, and it warps them seamlessly to form the long trunk and the torso of the tapir.
It understands the physical mechanics of an accordion.
And it maps those mechanics onto the biological anatomy of the tapir. It implies an incredibly high level of semantic abstraction.
It understands accordionness not just as a static object, but as a transferable property that can be applied to tapiriness.
It decomposes the visual world into attributes that can be mathematically recombined at will.
And that leads right into the next capability, variable binding.
Which cognitive scientists and linguists absolutely obsess over.
Right, because it tests syntax. The prompt they used was an illustration of a baby hedgehog in a Christmas sweater walking a dog.
Okay, so let's parse the syntax there.
You have two distinct noun entities, a hedgehog and a dog. And you have one specific modifier, a Christmas sweater. And the grammar of the English sentence dictates that the sweater must be worn by the hedgehog, not the dog.
Now, older bag of words models would just see the tags sweater, dog, and hedgehog and throw them all in a blender.
Usually resulting in a dog wearing a sweater, because dog in a sweater is a massively common trope on the internet. It's statistically much more likely than a hedgehog in a sweater.
But this autoregressive transformer actually respects the grammar. It binds the variable Christmas sweater specifically to the entity hedgehog and leaves the dog alone.
Mostly.
Mostly, yes. The authors are very transparent about the failure modes here.
It is not perfectly consistent. Sometimes the dog gets a matching sweater.
And my personal favorite failure mode? Sometimes the dog just morphs into a second, slightly smaller hedgehog.
I love that one. And the model just goes, I'm overwhelmed by the hedgehog context. I don't remember what a dog is, so here is a tiny hedgehog on a leash.
But the fact that it achieves correct variable binding, even a significant percentage of the time, it proves that the self-attention mechanism is actually capturing the hierarchical syntactic structure of the prompt. It's not just doing keyword matching.
It's doing basic visual logic.
Yes.
And then we get to perhaps the most spooky emergent capability in the entire paper, zero-shot image-to-image translation.
Spooky is the right word because the authors explicitly state they did not design or train the model to do this.
It is an entirely emergent property of the autoregressive stream.
Right. because the model just reads tokens sequentially, left to right. You can effectively hack the input stream.
Explain how that works.
Okay. You feed the model a very specific text prompt, something like the exact same cat on the top as a sketch on the bottom.
Okay.
Then, instead of asking the model to generate the entire image from scratch, you manually feed in the first 512 image tokens.
Which physically corresponds to the entire top half of the 32 by 32 grid.
Exactly. You give it a real photo of a cat for the top half. And then you just stop and say to the model, okay, you take over, autocomplete the rest.
And because it read the prompt sketch on the bottom, the model's attention mechanism looks up at the photo of the cat in the top half, extracts its specific features, and renders the bottom half as a pencil sketch of that exact same cat.
It's mind-blowing. Figure 14 details all the ways they exploited this.
It can do reflections. If you say upside down, it perfectly reflects the top image.
You can do localized style transfer. You can give it a photo of a cat and prompt it to finish the bottom half as a postage stamp, or add sunglasses.
It effectively taught itself how to use Photoshop filters just by reading the raw internet.
It mapped out the latent transformations between different visual domains entirely on its own.
It's incredible. But to be rigorous, we have to look at the other side of the coin. Section 6. Limitations. Where does this 12 billion parameter brain completely break down?
It has several glaring blind spots. First and foremost, it cannot count.
Right. If you explicitly prompt it for 3 sheep,
you might get 2 sheep. You might get 5. You might just get a nebulous interconnected cloud of wool and legs.
Why does it struggle with counting so much?
Because counting requires a very rigid, discrete, logical process that continuous pattern matching struggles with. It knows what sheepness looks like, but isolating distinct entity boundaries is hard for it.
It also struggles with spatial reasoning, right?
Very much so. Simple relational prompts like a red block to the left of a blue block are frequently flipped. It understands the objects and the colors, but the absolute coordinate space of left versus right is muddy.
And then there's the text rendering. This is always funny.
It is. If you ask it for a neon sign that says a very short word like backprop, it can usually do it.
But if you ask for a full sentence on a billboard,
it devolves into complete alien gibberish. It looks like text, the kerning is right, the curves of the letters look realistic, but it spells absolutely nothing.
It's exactly like trying to read a book in a dream.
That's the perfect analogy. The local coherence, the shapes of the letters, is intact, but the global coherence, the actual spelling and meaning, completely falls apart. It knows what written language looks like visually, but has no idea how to actually write.
So stepping back, what is the lasting influence of this paper? Why are we dedicating a whole deep dive to it in 2026?
Because it definitively validated the scale is all you need hypothesis for the field of computer vision.
It killed the bespoke, handcrafted architectures.
Completely. It proved that you don't need clever, domain-specific geometric tricks to generate images. You just need an incredibly flexible, general-purpose architecture, the transformer, and enough massive data to blanket the entire statistical distribution of reality.
It paved the runway for everything that came after. DALL-E 2, Stable Diffusion, Midjourney.
Every single one of them stands on the foundational proof of concept established right here. It fundamentally shifted the entire paradigm of the field from how do we mathematically model this specific visual object to how do we curate a large enough data set to feed this generic pattern matcher.
It structurally turned computer vision into a subfield of natural language processing.
That is a very profound and very accurate way to phrase it. It unified the modalities.
All right, that brings our main analysis to a close, which means it is time for our favorite segment.
Let's do it. The novel notions.
Time for the standard disclaimer. The following ideas are theoretical extrapolations intended for entertainment purposes only. Please do not attempt to build a startup on these concepts without rigorously doing the math first.
Seriously, do the math. Don't email us if your VRAM melts.
Idea number 1, I called this the universal semantic compressor for interspecies communication.
Okay, I am intrigued.
Here is the pitch. This paper proves that a discrete variational autoencoder can learn a universal vocabulary, those 8,192 tokens that successfully represent the fundamental physical atoms of visual reality. Shapes, textures, lighting.
Right, it compresses the continuous RGB world into a discrete semantic language.
Exactly. Now, consider whales and dolphins. They are highly intelligent and they live in a visual world. They have eyes. They see the exact same ocean, the same coral reefs, the same sharks that we do.
They share our physical reality.
Right. So what if we train one DVAE strictly on the audio spectrograms of human speech, and we train a second DVAE strictly on the audio spectrograms of whale songs, and then we use a massive autoregressive transformer to force a translation through the visual latent space. The pipeline is human audio tokens mapped to the shared visual context tokens, which are then mapped to the whale audio tokens.
You're using the visual representation of the physical world as the universal pivot language.
Exactly. We have absolutely no idea what the specific whale word or click for shark is. Their syntax is a total mystery, but we mathematically know what a shark looks like visually.
So if the model can accurately map the human spoken word shark to the visual token representation of a shark,
and then map those exact same visual tokens to whatever acoustic pattern the whales make when they are physically looking at a shark,
you effectively create a cross-species Rosetta Stone, where the common ground isn't grammar, but the shared physical geometry of the environment.
Yes, a zero-shot text-to-whale song generator.
You know, from a pure latent space alignment perspective, it is surprisingly plausible. Multimodal models today do exactly this kind of latent space alignment.
If you strapped a GoPro and a hydrophone to a whale to get the paired data,
you could theoretically align the acoustic space with the visual space. And since this paper already proved we can align text to the visual space.
Boom, we are casually chatting with Flipper.
The primary biological flaw in your startup pitch, however, is that a dolphin's primary conceptualization of a shark is likely acoustic via sonar, not purely visual via their eyes.
Look, don't ruin my unicorn startup pitch with actual marine biology.
My apologies. It's a very fun latent space theory. What is your second idea?
Idea number 2, recursive reality, authentication, the anti-deepfake protocol.
You definitely need one of those.
So we noticed in section 5 that the autoregressive model fundamentally struggles with variable binding over long contexts. Right?
The hedgehog sweater problem.
Right. And it also struggles with maintaining strict logical consistency in complex geometries, like reflections. Sometimes the cat in the mirror randomly has sunglasses.
Because the autoregressive drift accumulates the further down the sequence it generates.
Exactly. So we build a CAP-TCHA or a security protocol that actively weaponizes that weakness. To log into your secure bank account, you don't click on pictures of crosswalks. The system gives you a prompt with 4 nested layers of recursive variable binding.
For example,
upload a photo of a mirror reflecting a painting of a hedgehog holding a smartphone, displaying a live photo of the mirror itself.
And the user has to go construct that elaborate diorama.
No. The authentication system generates that image using the user's local AI agent, and our server analyzes the output.
Oh, I see.
A physical camera or a strict physics-based rendering engine like Blender maintains perfect 100% logical consistency all the way down that recursion rabbit hole. The optics math is perfect.
But a statistical autoregressive model.
By layer 4 of the recursion, the mirror inside the smartphone screen will probably just be a blurry picture of a dog, or it will lose the sweater.
The probability of maintaining perfect semantic consistency across 4 nested levels of attribute binding is effectively 0 for a probabilistic token predictor.
Exactly. It is a Turing test for physics. We rely on the fact that only physical reality is mathematically consistent. AI always eventually hallucinates.
So you use the inevitable hallucination drift as the cryptographic fingerprint of a fake.
We authenticate reality by watching the AI fail to simulate it deeply enough.
That is genuinely brilliant. You are exploiting the fundamental flaw of statistical learning, which is that it doesn't actually know the hard rules of physics. It only knows surface-level correlations.
And correlations always fade over distance.
Correlations fade over distance. You should put that on a t-shirt.
It's good, right?
I'll buy one.
Well, that wraps up our deep dive today. What a journey. We started with 250 million noisy, watermarked internet photos and ended up with a taper made of accordions.
It's a beautiful trajectory. Ultimately, it means the line between seeing and reading has been permanently erased. The machine doesn't see pixels anymore. It reads visual tokens.
And because it can read them so well,
it can write them. It can write our visual reality.
And we are all just living in the autoregressive output stream.
Let's just hope whoever's running the simulation doesn't crank the temperature setting too high.
Indeed. We'd start seeing a lot more hedgehogs. A link to the original paper is in the description.
Highly recommend reading it. It's a modern classic.
This has been TalkTensors.